Good morning, everyone. Hopefully everyone's doing okay. So just waiting for the speakers. I'm sure they'll be slowly joining in. And we'll begin in roughly 2 minutes. Thanks for joining us today. So we'll see you in 2 minutes. All right. Welcome everyone to the Journal Club / Showcase event in the Summer of AI. We're going to have a few talks today. And if you haven't already seen the calendar invite, which usually has the agenda in there, we will be covering transformers. So I don't know if you've seen the Slack post, have seen the email. Transformers are becoming incredibly important. Usually we try to cover the intro of the transformers and then go into the details, but these things are recorded. So if you're not that familiar with transformers, I urge you to check back to this session or have a go at the Friday session and then come back. Regardless, you should get a lot out of it to see how important transformers are. And today we'll be covering sort of a number of works related to transformers that push transformers into new areas. And of course, one of the most important reasons for covering the transformer is this new model called GPT and ChatGPT. There are various versions of GPT. GPT-3 has been quite incredible itself, but the chat version you saw does amazing things. So we'll chat about more. Oh, sorry, we'll talk about that more on Friday. But today we'll go through all the individual works that make transformers so awesome. Just a quick summary of what transformers are. We in the Getting Started series, we talked about neural networks and perceptrons. And when you have many layers of them, you have a multi-layered perceptron. So transformers can be viewed as a more generalized form of that. With an MLP, basically, once you train the network, the weights are fixed. The transformer can actually adjust its weights through attention dynamically, depending on the input. So that's why it's so powerful. All right, so I see the speakers are here already. So I think roughly, well, the way I was going to go was, so Marlon, who's hopefully here. Yeah, there he is.
Hey, Shakes.
Hey, Marlon. So Marlon is going to talk about work he recently got published in Transformers. And then we'll go on to Linfeng, who will cover recent advancement of using transformers for 3D imaging, which was published in CVPR outside UQ. So Lin Feng will be providing a sort of a journal review of that particular paper. So maybe we'll get started with those two. So Marlon, can you let's have your talk first, and if you can test your mic and share your slides, etc. We've got a great audience. Thanks everyone for coming. The session is being recorded, by the way. So Marlon is going to talk about a new way of representing images within transformers. All right, Marlon, take it away. Thanks.
Cool. Thanks, Shakes. So yeah, as Shakes said, it's a bit of a we're going to go into image tokens before we go into transformers, but I'll try and do a quick rundown of everything. So, of course, if there are questions at the end, please let me know, and I'll try and get a bit more into detail on some things. So as the title kind of suggests, we're going to be looking at transformer compressed sensing via global image tokens. And we'll get into what that actually means in a bit as well. But the idea is that we're going to be using this general type of architecture, which is a transformer neural network, to do, I guess, image restoration for MRI tasks. So again, another bit of a rundown before we get started, but MRI in general, you do your acquisition of data or your acquisition of your image in something called K-space. So this is our discrete Fourier domain, or if you're not familiar, it's a transform domain that has the constituent frequencies of an image. So on the image that we see on the left, it's our fully sampled case. The scan type, just sort of in this toy example, we'll say the scan time is 40 minutes. It's usually really quite long. But once we've collected the data from our MRI, we just do an inverse Fourier transform to get to our original image, or our target anatomy that we're trying to look at. So a way to accelerate this is to simply scan less of these data points. And that's sort of shown on the image to the right, where in this case, we'll say that the scan time is only 10 minutes or a quarter of the time. But hopefully you guys can see that taking the inverse Fourier transform of this leads to lots of artifacts. And something I'll say right off the bat is that these artifacts are really large, right? They're quite structured and they span, I guess, the size of the image. So the goal of compressed sensing is to develop a mapping between the undersampled K-space and the fully sampled image. Normally, this is done through, optimization techniques, but just sort of the gist of it is, in this particular minimization problem, maybe I will use the laser pointer. In this minimization problem, this component is our data consistency. It's sort of just saying that the reconstruction should sort of look like or contain data that is similar to the captured information. And the term on the left is the regularization, or the denoising component, right? This tells us what our image should look like. And so doing a balance between our denoising and our data consistency, we can hopefully get a good reconstruction. There are a few solutions for this. As I sort of said, it's an optimization problem, but we've also seen a lot of convolutional approaches to this particular thing. So where we have our noisy image, you do a bunch of convolutions to it, and we generate this mapping via these convolutional operations. So what is a transformer neural network? I guess kind of simply, I'll try and focus this more towards images. But the idea is that you get some sort of embedded representation of your image. Typically, at least initially, the approach for this image embedding is image patches, and I'll kind of visualize some things a bit later. But once you've got, I guess, an embedding or a representation of your image, it gets broken up into these tokens. So each patch is its own token, and it contains some information about the image going in. There are a series of operations, but the real, I guess, the real interesting part of a transformer neural network is this attention component. So once you take your inputs, so the embedded image tokens or whatever the embedding is, you split your data up into these 3 different inputs. And this is done using, a matrix multiplication, or it's just like a projection of our input data. And these are called the queries, keys, and values. And we do, I guess the equations here, we do it's a sort of a dot product between the queries and the keys, and then a softmax for that nonlinearity, and then another dot product with our values. And the idea with this is that each of our inputs is being, I guess, projected or changed in some way, hopefully to be more informative to the problem we're trying to solve. And the idea of this attention mechanism is to try and figure out what the relationships are between different image patches, right? Because this particular operation goes between every single patch in the image. And this is quite powerful because it means that, you know, a token or a patch that's in the top left corner of an image is still sort of interacting with a patch that's in the bottom right corner of the image, right? It's got a very global structure to it. And yeah, I think maybe we'll leave it to questions later if you guys want more info, or there will be later talks about getting more in detail about how all this works. So which tokens are actually available to us? And I think this might be a more useful slide. The initial one that was kind of proposed for object detection was image patches. So with the idea that we can take an image, break it down into some patches, and then feed it to a transformer, right? So this linear projection, that's just sort of embedding the tokens in something that makes more sense to the transformer. We then concatenate, or we add some sort of positional embedding to our tokens. So something that'll come up a bit later is that these transformers are really general purpose. And just because of their structure, they don't actually know where the patches come from. So this was a really important step, you know, give it the patch, as well as some sort of embedding that tells the transformer exactly where that patch came from, right? And then you do the multi-head attention stuff, and then you get some sort of classification for what's in the whole image. Again, where each token is just in a patch of the image. Something that came a bit later and has kind of been shown to be a bit more, well, it's across the board, it's sort of showing to be a bit more powerful in image representation or object detection stuff than these image patches. And it's simply just taking an image and breaking it down into its columns. And then instead of doing attention on patches, you actually do attention across the columns of the image. And then you do attention across the rows of the image, right? So sort of a column-wise attention and a row-wise attention, which is why it's called axial tokens. Yeah, cool. So that's that one. And then one that's actually really quite interesting that I think has been getting a lot more investigation, I think quite rightfully so, is early convolutions. So the authors of this particular paper recognize that, well, each of my tokens or each of my patches, if you think about it, is just a really long strided convolution, right? I have a window, and then I do a stride, and then I have another window, and then I do a stride. So they kind of realized, well, what if we just trained an actual neural network or a CNN to generate these tokens for us that then the transformer can, I guess, operate on? It's sort of like curating the most important features of the image. And again, this has seen really quite good results so far, but it, yeah, tends to have high penalty or high cost penalty. So in general, just TNN, transformer neural networks and convolutional neural networks, how do they compare? Well, I'll kind of discuss this in terms of the limitations maybe. So the CNNs tend to be they've got quite a strong inductive bias in that they kind of have to operate on 2D neighborhoods. So a very local structure. They also have translation equivariance, which can be a good thing and a bad thing, right? Because of this shifting window approach, doesn't matter where in the image something of interest is, it's always going to have the same response regardless of where it is. But because of this, it can be really difficult for us to model long distance relationships, right? So again, sort of like our transformer, how I mentioned that the attention mechanism can, I guess, communicate between patches at really long distances. Convolutional neural networks really struggle at this, right? Because of that sliding window, 2D neighborhood, and translation equivariance structure. Transformer neural networks, on the other hand, lack this inductive bias, which can actually make training really difficult, right? Convolutions are really quite natural at processing natural images, whereas you kind of have to force transformers to do the same operations. Vision transformers, so what we've been discussing so far, require usually quite a large number of parameters. And then even though we've got this attention mechanism, because I guess historically our input tokens are just patches or columns or rows, global image structures are actually still kind of difficult to model from the patches. And I guess that is the crux of what the rest of this paper is going to try and address. So just kind of briefly, I'll try and summarize. We've got a target image that we capture using the Fourier domain or the K-space. We undersample this using some sort of a mask. and then we take the inverse Fourier transform to get a noisy image. In the case of transformers, if we're trying to use them for denoising, the patches are going to look something like this. And the reason I've kind of disordered them in this sense is hopefully so that you guys can see that while the artifacts are sort of similarly present inside each patch, it's actually kind of difficult to figure out what line matches up with which line, right? What structures match up with which structures. Is this noise or is this just part of the image, right? So even though the attention mechanism exists, it's still not, I guess, naturally designed to deal with this sort of artifact. And so our solution to this was something called the kaleidoscope transform. If you guys have been playing around with CNNs a fair bit, you guys might know this as the pixel shuffle or the pixel unshuffle operation. And I'll have a visualization in the next slide on how it operates. But just here, hopefully you guys can see that all of these artifacts are kind of spread around the entire image. Because of this kaleidoscope transform, each token, right, which is these low resolution copies of the image, each token now actually contains the exact same artifacts that are in the large image, right? So the intuition here is that sensing, we generate these really large artifacts that can be confused for just, image structures. And so we've developed this image token where each token contains the same structures. And so hopefully we'll make it easier for the transformer to denoise all of the unwanted artifacts. So how do we actually get kaleidoscope tokens? This looks a bit scary at first, but hopefully it's okay. So I'll break this down into, I guess, little quadrants. So this kind of indicates the y-axis numbers, x-axis numbers. So this is the y and the x. And so here, if we break this down into little 2x2 boxes, you can hopefully see that the top left pixel of this 2x2 box goes to the orange box. The top right pixel goes to the green box, yellow to yellow, and blue to blue, right? And then if we then shift over to these group of 2x2s, the top left pixel goes here, top right pixel goes there, and so on, right? So if we kind of look at all the oranges, we can see we're getting like a subsampling of the image, same as the greens and blues. And then with the kaleidoscope transform, you sort of concatenate them on themselves, and they can be treated as their own individual tokens. And then just here, a quick comparison. The idea with this particular work is that we change as little as possible about the transformer itself. So instead of feeding in these patches, we feed in tokens, right? That transformer part is the exact same as the vanilla vision transformer. The only difference, again, is this token embedding, which is the kaleidoscope transform. And the really interesting part is that, unlike convolutions, this doesn't have any additional penalties, right? This is just a pixel reordering and like selecting the right ones. And this is the exact same. So in terms of computation time, these two are equivalent. Again, it's just that one has local patches and the other one has these global kaleidoscope tokens. And then this table is actually, I think, quite important. It's what can we actually see with each token embedding. So with the patch case, it's maybe the easiest for us to visualize. The image scale is inherently local, right? Each patch can only ever see a small window, but the frequency scale is inherently high, right? Everything that's inside the patch has to happen inside the patch, right? So it has to be, for us to see it, I guess, it has to be a really high frequency or texture information. Whereas the kaleidoscope tokens, right, they're low resolution copies of the original image. So kind of inherently, the frequency scale that is embedded in this token is low, but the image scale is global, right? Every single token is just a smaller version of the original. With axial, again, it's local because we're getting either columns or rows of the image, but the frequency scale is both low and high, right? It's sort of the columns and the rows span the entire image, so they kind of inherently contain low and high frequency information. So in the past, usually, transformers will choose one of these, right? They'll choose axial tokens and solve the problem. They'll choose patch tokens and they'll try and solve the problem. Our idea, like as an additional, is sort of proposing that, well, what if you just combined all of your tokens, right? Each of these is inherently limited to seeing a particular aspect of an image. So combining them in a single network should hopefully improve your performance, right? Going axial, then kaleidoscope, then patch, you'll do a local processing with low and high frequency scale operations. You'll then do a global operation, and then you'll finally do a like low down texture-wise denoising of the image. The general structure for this is kind of existing from a 2017 paper where they had convolutional neural networks doing denoising between data consistency steps. The only thing that we've replaced is the CNNs with these transformer neural networks, with the idea that this E, or this embedding, can be any one of the ones that we've just proposed. So the patch, the axial, or the kaleidoscope tokens. And so you kind of get your noisy input, you do some denoising, you do data consistency, and you keep repeating that process until eventually you're happy with the result. Cool. So in this particular test, we only studied with a single data set, which is a brain data set from NYU. Not really too important, but there were a fair few images, and we compare against two convolutional alternatives. So again, we compare against the exact same structure, except with a CNN in the particular network pipeline. And in this case, D5C5 is a smaller version and D7C7 is a larger. And these are our quantitative results. So the top two, again, are the convolutional versions of the network, and the bottom four are the transformer ones. With the patch, kaleidoscope, and axial, each of those three implementations only have those token types, whereas our ensemble, as we discussed, does axial denoising, kaleidoscope denoising, and then patch denoising. Something quite interesting is that the number of parameters for the convolutional networks, as we've kind of discussed, they're inherently smaller. There are many, many fewer parameters in these CNN implementations, and our transformer models have a lot more parameters. But because we're not doing any sort of shifting window thing, there's not a lot of RAM usage, the actual execution of the networks is faster. So minutes per epoch is considerably faster than these convolutional alternatives. And then as well, of course, we do see performance improvements. So with the patch case, we get not better performance than the CNNs, right? The CNN always performs better than our patch transformer. Our kaleidoscope transformer is able to sort of slightly improve the performance compared to the patch alternative. Again, the axial just by itself has the best performance, though it is noted that they have got also about 10 million more parameters just because of the nature of the structure. And then the ensemble network, which combines all of these three denoising types, actually performs the best overall, even beating the, I guess, image designed convolutional networks. And I'll get into, I guess, the R4 results in a sec, but these results are a little bit misleading. So PSNR should be high, I guess, and SSIM should be high as well. I should have mentioned that at the start. And quite clearly at R6 and R8, the results from our transformer is better. But even though these numbers say that at R4, our convolutional versions are better, I'm going to show you guys in an image next that kind of shows otherwise. And then just quickly, here's a validation loss, like comparison between the training of these transformer networks. So again, sort of the same pattern. The patch does okay, but just the kaleidoscope only network performs a bit better, right? That's the only thing we've swapped. It's got the same number of parameters. The execution time's the exact same, but just swapping the tokens from patch to kaleidoscope, you get a free performance improvement. Using axial tokens performs even better still. But again, I'll note that it has about 10 million more parameters. And then the ensemble, which actually has the fewest number of parameters, performs the best overall, right? And again, it's due to being able to process local and global information sort of independently within each token. So this is what I was mentioning about the qualitative assessment of the images at reduction factor 4. While the convolutional versions have really high PSNR scores, even higher than the ensemble, hopefully you guys can see that these kind of faint noise-like image features disappear from the convolutional versions, right? It's quite difficult for them to distinguish from this noise whether or not there are two separate structures. Whereas because the transformers, I guess, are kind of designed to look at the image as a whole, it's a bit easier for them to kind of distinguish where things should be. And you can kind of see this here, right? The axial and the ensemble networks can both see that there's two veins kind of operating separately in this particular image. And the results are the same for R6, right? Axial and the ensemble network, they can both sort of see these two structures, whereas the convolutional networks just cannot. And then again, you see here that just swapping from patches to kaleidoscope, we do get, again, a performance improvement in the case of compressed sensing. And then in R8, again, we get the same thing. Cool. So future work, have I just shown that convolutions are a thing of the past? Well, I don't think so. I think that it's, as we've sort of seen, we've had to do a combination of tokens just to get to the performance level of a convolutional neural network. So what I think and what has been shown over the past few I guess, years that vision transformers have been out, is that a combination of a CNN and a TNN should result in the best performance, right? Transformers can do a lot of global processing. So why are we forcing them to do local high frequency operations? And then on the flip side, convolutional neural networks are really good at that stuff. You know, they've got that inductive bias. They're kind of good at processing local 2D information. Why are we forcing them to operate on a global image scale in some applications? So the idea here for future work is to replace this particular structure, where you've just got a transformer neural network that does the denoising, with something that looks a bit more like this. You take your undersampled image and you take the kaleidoscope transform, right? In this case, you kind of end up with these 4 low resolution copies. You then use the transformer to denoise each of them independently, right? Each of these are low resolution copies. They've got only global scales. We've kind of gotten rid of the low frequency components. And so that's sort of what we've seen that the transformers can specialize at, right? They can denoise these quite effectively at this smaller resolution. You then combine this with a convolutional neural network denoiser, which does what I've called a cross-channel denoise. So each of the convolutions goes through each of these tokens to try and do the local denoising of the image. And then at the output, you do the inverse kaleidoscope transform, and you get the final not noisy image. And kind of interestingly, you've got the exact same ensemble network as before. You've got the small ensemble network that I've just discussed. And it turns out that even though we've reduced the parameters from about 30 million to just 1.1 million, we can actually see a performance improvement by combining these transformers with the convolutional neural network. The only thing that takes a hit is the computation time, right? The inclusion of these convolutions does slow everything down. But if you guys remember, it was about 14 minutes for the original D5C5 implementation, I think. So even though we're in, more time required than the full transformer network, I think just by reducing the parameters by about 30 times and seeing a performance improvement, this sort of architecture is really quite interesting to pursue. Cool. So those are some of the references. And thank you very much for listening.
All right. Thanks, Marlon. That was great. Do we have any questions for Marlon?
There's a hand.
Is it clap?
Oh, is it a clap? Oh, thank you.
Oh, hey, Martin.
Hey, Wei.
Yeah, I have a question regarding to your experiments there.
Yeah.
So can you go back to the page 13? Yeah, this one here. So do you have the inference time for each of the models there?
I don't actually. That's something that I didn't grab for the paper, and I haven't gone back to check.
Right. Okay. But do you have like rough ideas how fast the transformer is?
I think. No, I'm so sorry. I remember checking, but I don't actually remember what the numbers are. I don't think they were too dissimilar. I think it was just because during training this, like, it just took a whole lot of memory for the convolutional ones, which kind of exacerbates this difference. But during execution, I don't think it was that different. But I still think the transformer was less than the convolutional version. But I'll have to double check that for you.
Yeah, thank you.
Yeah, always worth keeping track of inference times. There's certain approaches when there's always a trade-off between memory, computation, inference, and training. And sometimes inference makes a difference in where you can deploy it. So for example, some networks use a less memory, will train faster, but they have massive inference times, which make them impractical in medical settings, for example. So yeah, worth going back. Good question. Worth going back and trying to find out. And there could sometimes be that having faster inference is a good advantage for your approach. Cool. Thanks, Marlon. I think we'll move on to the next talk. Thank you again, Marlon. Our next speaker is Lin Fong. She's there.
Hi, Shakes.
Hey, Lin Fong,
Hi,
thanks again. Yeah, so if you can share your slides and things.
Yep.
So Lin Fong's going to talk about a CVPR paper. So CVPR is one of the foremost avenues of publication in science in general, and CVPR is the #1 for AI. And so this was a paper in last year's CVPR. And of course, it's from some other area, but Lin Fong is going to, luckily for us, he's gone through the paper quite in detail, and he's going to share his findings with us. Thanks, Lin Fong.
Yep.
Go for it.
Hi, everyone. So as Shakes mentioned, I'll talk about this CVPR paper. So basically, they combine the advantage of CNNs and transformers on medical imaging classification task. Okay, and so the motivation of this paper is that there are many 2D CNNs everywhere that they do classification on natural image, and they achieve really good results. So they want to take advantage of these pre-trained 2D networks. But these 2D networks have some disadvantages, because they can't, when you use these on the 3D images, they can't discover 3D features. Well, there are also some 3D CNN networks. We can use it for 3D. We can use it to learn 3D representations, but there are very little publicly available 3D data sets with pre-trained networks, because 3D images are very limited. And on the other hand, transformers compared to CNNs, they have a wider receptive field, so they can cover large area of images and grow linearly with the depth of the network. So, and the traditional convolutional neural networks, they have limited receptive field. So how do we combine the advantages of these 2D CNNs, 3D CNNs, and transformers? So this is the motivation of this paper. And the novelty of them is that so they successfully combine the CNNs and transformer architectures for 3-dimensional image classification. And the way they use CNN is that they want to find the local features and the abnormals of the Alzheimer's disease. Okay, and the transformers, so they utilize the advantage of since they have a larger receptive field. So they use that to study the multi-plane of the 3D image and the multi-slice tokens obtained from CNN to capture the long-range relationship within the 3D MRI images. And they prove that it is more efficient when we combine the 2D and 3D CNNs with transformer as a classifier. Is showing better results than just use this separate networks. And finally, they visualize the activation area in the 3D MRI images and can be considered as interpretable results. Okay, and the task they are working on is simply classify Alzheimer's disease from cognitive normal. So you can see here on the right, the control normal case, the ventricle region is relatively small than the AD patient. Okay, so if patient get AD here, the ventricle region should get larger, and also the hippocampus region as well. So hippocampus region is here and here, and they also get larger, and also the cortex region. So your gray matter and white matter should have some loss in here. So basically, we want the network to pick this up and correctly classify the patient, whether or not if it's AD or cognitive normal from a 3D MRI. And the network architecture looks like this. So it looks a bit scary at the beginning, but if you look at it, so from here, a 3D image gets into a CNN, So here they don't do dimensionality reduction. So for example, 128 get by 128 by 128 gets in. It will become, the size will still the same, but with more channels. Okay, so that's what's happening here. And you know, you will have 3 dimension and 3 different views from this 3D image. So what they do is that, so this is the part where they use the 3D CNN. And after that, they take from each view. So for example, this coronal view, they take the same slice as the width. So if it's 128 here, they take 128 slices from the coronal view, and same for sagittal view and axial view. So they take 3 patches of the view of the slices from this 3D brain, and they put into this 2D pre-trained CNN. So that so this is just simply a ResNet they used in the paper and pre-trained on ImageNet. So they utilize the 2D information here, and then they pass through a nonlinear projection. So this one here is used to get these slices. These slices fit the transformer dimension. And the most important part here is that they created this, they call it like positional and plane embedding tokens. So this embeddings will give the transformer information of which slice. So these slices, which plane are they from? Okay, basically gives the spatial information. And they use a similar class token from the vision transformer at the beginning. So in the end, after you train the transformer, this class token will goes into a dense layer and then do the classification task. Okay, and let's take a look at detail of the network. So first, this 3D image will be passed through this 5 by 5 by 5 3D CNNs with batch normalization and activation layer. So they do this twice, but remember, like previous mentioned, they don't do the dimensionality reduction. And here's the next step. They take the slice from each view, coronal view, sagittal view, and axial view, and fit into this 2D CNN. So 3D information is obtained here. 2D localized information is obtained here. So this part, this CNN bit is learning the disease characteristic, okay? And then here, after the 2D CNN, they pass through this nonlinear projection. So this just consists with like 2D CNN and then MLP layers. Basically, they are just dense layers and activation layer. So they made this dimension the same as the transformer dimension, okay? And next one, which is the most important part, is that after they have these, you know, nonlinear projection of the slices, they have class token, this separation token. I'll explain this in a bit, and then pass through the plane embedding, and then the normal positional embedding. So what's happening here is that these are just the slices from the previous layer, and then these separate tokens basically are just, you know, numbers. So here can be 1, 2, and 3. Okay, and but like remember here before they will be like embedded into 256 or some other value. Okay, and this class token is just randomly initialized. And this plane embedding are basically, so for the slice from the same plane, they are all the same. Okay, this could be 1, 2, 3 as well, and they also pass through a nonlinear projection, so embedding layer, and this is just a normal positional embedding. So this one is learned instead of the, you know, the sinusoid one. So they add these values together to give the transformer information of, okay, where are these slices from? Okay, this this part is from the coronal view, sagittal view, and axial view, so that all the information extracted from the CNN part will be also passed through to the transformer. And lastly, here is just a normal transformer encoder, consists of the embedded slices, which is here, and then a layer normalization, multi-head attention layer, which Malone mentioned, just study the correlation between pixels and between slices, okay? And then MLP layers for classification, okay? And let's look at some results. So the results they've shown here is that, so they compare with their work, with the state of the art or like well-known CNN networks. So you can see here, so they also tried the ResNet 50 with transformers. So in most cases, adding transformer will help to increase the accuracy. Only the DenseNet here, if you add transformer, it has a slightly deduction. And I want to highlight here is that if you use a 3D VIT, so fully transformer network, they actually got a decrease of the accuracy here. And the reason is that, so I think because the transformer is learning the long range, dependence from the image, and then it cannot focus on the localized information of the disease. So when you have the combined model, for example, this ResNet with transformer, it can both capture the long range information and the localized information. That's why the purely transformer based VIT, 3D VIT is not as good as the other ones. And so they use so they combine 3D information, 2D information, and transformer global information and achieve the best results. And they test on 3 data sets, ADNI, ABLE, and OASIS, and all achieve the best results. And also they've shown some ablations. So you might wonder, okay, what if I remove the 3D blocks? What if I remove the 2D blocks? So they've shown here that if by removing the 3D scenes, it's not as good as combine them together, okay? And yeah, and it happened to all cases. So fusion model is worked best. And then they also show that okay, how about I just use one plane instead of multi-plane? And 3D planes will always provide more information because the pixels are related to each other, can always help transformer to learn the the long range information. Okay, and then the interpretable results they've shown. So they generate this activation map from a published work, also from CVPR. So you can see here that, so with the probability of 93, this case is 80, and the network pick up the same region that, those clinical paper found that if the people get Alzheimer's disease, these regions will change. So hippocampus area, they show that this red region, the transformer pay more attention, okay? And they do the classification based on this. And also the cortex region, this cerebellar region, oh no, I mean this part also be picked up. So it's related to hippocampus as well. And this ventricle, so ventricle enlargement is also very important. They also pick that up, okay? And it happens to all other data sets, okay? And you can see here is a large enlargement that they pick it up. And also here the cortex region, okay? And yeah, so that's all from this paper. Are there any questions? So I think this paper it's a simple idea, but it's very efficient, okay? I think that's why they got into the CVPR.
Okay, thanks. Thanks, Linfeng. Any questions for Linfeng? I know you've, maybe I can start. I know Linfeng, you implemented this. What was the most tricky bit that you found that was hard to implement in this?
I
Just
think
lots of
it's
little bits or one key thing, a few key things?
so I think it's here, this one. So in the paper they didn't clearly say like how they encoded this, separation tokens and these embedding layers. So here at the beginning, I thought it would be just some random values that let the network to learn itself, but actually they just give a specific fixed value here to do the separation.
Right, yeah.
Yeah, and another one is how they extract these slices from different view. So each block here is a 128 by 138 by 128. So it's just from different angle. So here is like 3n by d dimension. So they took 3D. So from each view, they take the same slices, same amount of slices. So I found it's a bit hard to get right here as well. So I think that's two key. And then yeah, the rest are very simple. I think here is just normal transformer encoder layer, and here is just pre-trained 2D CNN here. So yeah,
Sorry, I might have missed it. What was the positional encoding used? In DC?
positional encoding here is just a learned one.
Oh, learned one, okay.
It's not the sinusoid one. It's just a learned one, and these ones are just 1, 2, and 3, but encoded ones to give the plain information.
Okay, cool. Any other questions? Does anyone else have any other question?
Sorry. Yeah, I think I have a question for the last slide.
Yep, thank you. This one?
Yeah, so if you look at the visualization here, it seems like when transformer is looking at the image, at the input from different view, for a particular view, it's actually doing something similar across the image, is it? Like for the chrono, and you can see it's always
Yep.
looking at those 4 sections there. Top left, top right, bottom left, bottom right. But for the sagittal, it's always looking at the very top and bottom.
Yeah.
Did they discuss anything about this in the paper? Like, is
I
this
think it.
yeah.
So this is kind of what they would expect it, because after training, the network will focus on this region where it gets enlargement, right? And these are the like when people get AD, the hippocampus and ventricle region, they always get enlargement. And from this case in particular, you can see here is actually missing the gray matter and white matter, and also the hippocampus region enlargement. And also from the sagittal view, for example, let's take so here, here, usually you would, so for this patient in particular, you can't see like the enlargement in the cortex region, but you can see a significant enlargement in the ventricle area, right? And the hippocampus area. And for the coronal view, so for different view, the network will see different places, because for other parts you wouldn't necessarily to see the change, if that answers the question.
Right. Yeah, I guess it's because I don't have much information about AD. So I'm probably just trying, my question is like, is this like a good detection based on the image you have there? Because based on the image you showed before, when people having the AD, pretty much all the components kind of shrink. So, but in the image here, it's only focusing on a particular part of the image. Do you think that's a good, like a good location that the transformer is looking at?
Yes, it's actually really good, because let's say like you mentioned they look at the same place, but actually for this coronal view, you can see they focus on the like this ventricle area, but for this one, it focuses on both ventricle and hippocampus area, because the hippocampus in this image in particular, it doesn't show up.
Right.
So this algorithm is actually really smart and accurately pick up the region. And so these ones are generated from different views, right? So they're not necessary to show like all the characteristic of ADs did not always show in different view. So you can see from these ones, they pick up these 4 areas, but for this one, they pick up this area. So I think this is really good. And also here, the ventricle is picked up, and also this hippocampus region also picked up instead of so not same as these ones. So the network should focus on these regions if they want to classify AD correctly.
Okay. Yep. Sounds
Yep.
good. Thank you.
Thank you for the question.
Thanks, Linfeng. And thanks, Wei. All right, I think we'll move on to our next speakers. Something completely different. How transformers and attention are used for graph neural networks. So I think Lou and Guyan are going to be talking. So is Lou there? Yep, there she is.
Yeah.
Hey, Lou.
Hey, Shakes.
Hi, yeah, share your slides whenever you're ready.
Yep. Okay.
And I think Guyan's going after you, I think.
Okay.
Yep, all right, go for it.
Yep. Hello, everyone. I'm going to talk about the graph attention networks, and you can find the paper from the link. And they are an important variant of graph neural networks that use attention mechanism, which is well known in other machine learning fields. Now let's start with a really short description on graph neural networks. And for a graph like the one shown here, each node can be described with a node feature vector. For a molecule, this feature vector would contain information about the items, and for a social network, attributes about a person, for instance. And regarding the structural information of the graph, we have the adjacency matrix. The adjacency matrix tells which nodes are connected. And the graph neural networks follow a message passing rule. The general formula describing the update of a single node embedding looks like the one shown here. And later we will see how we can extend this formula to use the attention mechanisms. And the node features are transformed by multiplying with a shared weight matrix W, as we can find here. And this is a learnable linear transformation, converting the node features into higher level features. Essentially, that is where the learning takes place. The weight matrix comes from a fully connected neural network. In other terms, when multiplying with this weight matrix, we simply pass each of our node features through a single linear neural network. Now, for each individual node, we want to do that only for the neighbors, and then sum them up into one embedding. That is the sum in the formula. Here, the I is the current node, and the G and the J are all the neighbor nodes of that specific node. And finally, in the formula, there is an activation function that is typically applied. Here it's called sigma. So this basic overview shows how the first layer of our graph neural network could look like. And the output are the updated node embedding H prime. This node that contain the information of all their neighbors. And for every other layer, we would now have a different shape of the node embeddings and the weight matrix, as we would use this embedding as the new inputs. And now let's find out how this process can be extended with the attention mechanism. And the basic idea of the attention in graph neural networks is to additionally learn how important nodes J's features are for node I. This importance is called the attention coefficient. We can see it as a weight for each edge of the neighbors that tells us how much attention we should pay to that specific node. This is the basic formula, how we can calculate them. And like we can find here, and for Hi and Hj are node feature vectors that are multiplied with the weight matrix. And A is an attention mechanism that returns the attention coefficient. And in order to compare the coefficients for different nodes, we need to normalize them. And this is simply done using the softmax function. The normalized values are then denoted with alpha. And we could compute the attention coefficients for all node pairs, but we can only focus on the neighbor nodes. If we do that, it's called mask attention because we mask out all of the other nodes. So now let's have a look at what this attention mechanism does. First of all, there exist many different possibilities for calculate these attention coefficients. There are so many choices that we can choose to formulate the A here. So the method chosen in the paper is just the one possibility. And in the paper, they simply choose a shared single layer neural network. The input for this network are the two transform node feature vectors for an edge. For instance, like here from the graph structure between node 1 and node 2. And the output indicates the importance between these nodes, the attention coefficient. This can be calculated for each node pair expressed as a formula. This is how the full attention mechanism used in the paper looks like. And most parts are already familiar to us now. And we see the normalizing using the softmax function. And we recognize the two transform node embedding we pass in as inputs. And these two node feature vectors are simply concatenated. And so these two pipes are the concatenation operation. Then we pass them through a single layer neural network. It means nothing else but multiplying them with a weight vector. And additionally, we see that leaky ReLU activation is applied on each of the outputs. The reason why this is done is that we want to emphasize the positive relationship between nodes. This means we cut off pretty much all of the negative values and just we keep the positive values. So this is the leaky ReLU activation. So now we know what attention coefficients are, and but how to calculate them, and how do we include them in the graph neural network. The way how this is done is simply by multiplying each of the neighbor states with the corresponding attention coefficient for that edge. And this can be seen as a linear combination of the node feature vectors weighted with the importance for each node. And as a result, the important elements amplified and the less important ones are suppressed. And yeah, that's all about the algorithm. And thanks for listening. And any questions?
All right, thanks, Lou. Do you know what sort of performance gains they got in what data sets they used?
Yep. I didn't put it there because but I can show you from the paper.
Yep. Anyway, we might. We might move on. I don't know if there are any other questions from the audience.
Yep.
Yeah, that's okay, Lou. I think we might move on to Guyan, and I think he's going to talk about a sort of graph attention networks, but also some improvements that have been made with graph convolution as well. So Guyan, yeah, thanks, Lou, for the talk. We'll move on to Guyan, and if Guyan can share his screen and start your presentation. Thanks, Guyan.
Yeah, sure thing. Thank you, Shix.
Great.
All right. So, yeah. All right. So I'll just talk a little bit about graph convolution, but nothing much because Lou put a really good foundation on it. And then I'll talk about an improved implementation of graph attention, which is called FTGAT-II, fast dynamic attention with initial residual and identity. So basically, if you try to understand where graphs are in the whole space of machine learning data, this guy standing here on the right, that's BERT. So BERT is an improved transformer version that you use for text. Text is like one-dimensional data. So then if you look at images here, it could be considered as two-dimensional. A picture is a sphere. If you think of video, that can be taken as three-dimensional. So you use all these convolutions, ResNet, all that stuff to process that vision or images. Graphs come onto the extreme other side because it does not have a notion of dimension. So it can be like n-dimensional, multi-dimensional, because a node at one extreme end could just connect to a node at the other extreme end, just one dimension. So that basically means there is no concept of dimensions there. It can be as abstract as it wants, and it can also generalize to images and text if you want. So graphs are kind of used in a lot of areas. So this is a few examples. Because the recording is there, you should be able to like grab the links. I'll not spend time on this. And so let's see how graphs and graph neural networks essentially work. So there is actually one graph here. So you see four different different arrangements of the nodes, but essentially that's one graph in four different arrangements. So what we do in graph neural networks is basically create something called embeddings or representations so that all the greens stay together, all the reds stay together. So there's some semantic or meaningful arrangement. So all that a graph neural network does is learn some encoding function so that you can arrange the nodes in some meaningful way. Like maybe ice creams and donuts are sweets. Maybe chicken and beef are meat, some kind of semantic arrangement. So this encoding function is the all important thing, and that's what a graph neural network does. So there's two ways of doing this. One is convolution. The other one is attention. So attention is the concept that Lou was explaining. The only difference between attention and convolution is in attention, you actually learn the importance of your connections. So these are the connections. So if you take this node here, node 1, it has neighbors 5, 3, and 5, which are like different classes. So all the graph attention will do is it will learn the importance of the neighbors and just combine information from the neighbors. So that's very important for what we are going to see in the next few slides. Graph convolution is a little more simple and basic. It will not learn the importance, it will just combine. So what this guy does in graph convolution is just combine all the information from the neighbors, assuming if you are connected to somebody, you have some similar features. So if you're connected to your mom and dad, you probably inherit something from them. That's a basic concept in graph neural networks. Attention takes it another step ahead and try to actually learn how important is your mom's features to you and how important is your dad's features to you. But end of the day, it's that aggregation of the features. So once an encoding function is learned, you can do a whole lot of stuff like classification, community detection, prediction, all that stuff. So this draws a lot from convolution. So if you look at here, this is a standard image convolution block. The same thing has been extended to graphs, and it uses the same similar pixel-wise attention aggregation thing for graph convolutions. Here's a little bit of math, how that's done. You have the features, you just add them up, and that's it. So if you write this in a matrix form, there's a very nice, compact, efficient representation, and that's just it. This is the adjacency matrix, the same thing that Lou explained, which gives the connections. X is your collection of features, and W is a learnable weight matrix. I just included this slide so you can actually see how the scale and normalization takes place. That's needed for like stabilizing this, but it's essentially that aggregation that takes place here. And then here is the math. It's the same thing that Lou explained with the attention coefficient here. So there's two problems in graph neural networks. One is that the notion that you are related to your mom and dad. That typically holds, but also there are cases where that does not hold. There's like, for example, a whole set of data sets like friend networks, dating networks, protein networks where opposites connect. And because of that, if you aggregate your connections in a graph, you're going to end up with the wrong information being aggregated onto you. That's one of the bigger problems in graph neural networks. So this illustrates how that works. So in graph attention, you aggregate everything. But in doing that, graph attention has two problems, because you are trying to learn the importance of your neighbors. What do you learn if none of the neighbors are important? That's a problem. When that happens, graph attention actually fails because there's no one to learn from, and basically nothing can be done. So because of that, if you look at the blue data set here, that is a set of data where your neighbors are similar to you. And you see that graph attention and graph convolution is very good. But if you look at the red data set here, that's a set of data where your neighbors are not similar to you are. And you see that MLP performance is way better than graph convolution or even graph attention. So how do you fix this? Another problem you have in graph neural networks is a problem of adding layers. So if you look at something like ResNet or like any image processing machine learning model, you have multiple layers. I think ResNet has something like 50 layers. And if you look at other models, they are over 50 layers. So you need the layers to get depth because that increases the power of the neural network. But in graph neural networks, if you go more than 2 layers, the model starts to do this, what you see on the animation here. So initially you have 3 nodes, 1, 2, 3, but when you keep increasing the layers, it all averages into the same thing. Representations deteriorate into looking alike. So we call it oversmoothing. So if you look at all these models here, all of them show significantly high oversmoothing. Graph convolution seems to be the better tolerant one because the mean average distance between two graph nodes seems to not deteriorate into each other. But in most of the other models, the nodes deteriorate into each other and the distance between the nodes are very small. They're getting closer, looking alike. So how can this be fixed? So in our paper, FTCAT-II, which stands for this, we do 3 important changes. The first change we do is we give a safety net or a fallback. Remember, graph attention learns an importance weight of your neighbors. What do you do if there's no important or relevant neighbor? There's nothing to learn. But what we do is we provide a default fallback. A copy of yourself is given from an initial previous layer, so that if none of the neighbors are similar, you can still fall back on your previous twin, kind of. The next improvement we do is we replace attention with what we call dynamic attention. So if you look here and try to remember the same equation that Lou presented, attention has a weight and a learnable matrix, but because you use them in this manner, it can actually deteriorate into a single weight matrix. But dynamic attention adds the same nonlinearity between the two weights. Because of that, it has been shown that it is more expressive and is more universal and able to learn a better relationship function. The third thing we do is just improve the regularization. So it has been shown that smaller weights are better. So by adding identity and W with a hyperparameter, we keep the W values or the weight values low, which means the model is more stable and faster to converge. That's a model. So it has those features we described. This is the initial representation or the safety net. So the safety net is added with an alpha component, alpha percentage. That's the attention module that uses dynamic attention. And this is the weight regularization where we try to keep the weight value low by adding the identity with the beta percentage. Yeah, so that's a model. This is the results. So if you look at the results, remember the blue is where your neighbors are similar and we are getting near state-of-the-art results. And red is where your neighbors are not similar and we are again getting state-of-the-art results in half of them. We are also able to do what we call inductive learning. So inductive learning is where you learn on data that has not been seen before. A comparison with some benchmarks. So graph attention is this orange guy, and when the number of layers increase as expected, its accuracy drops. But because we have added the safety net and dynamic attention, we are able to sustain up to 32 layers. So this is the first, and as far as we know, the only attention-based graph neural network that can have over 16 or up to 32 layers. A little bit more on the data, but you could have a look at this on the paper, I guess. More stuff. So the blue stuff is our model. So the left top, that area is where you should be or is preferable to be. And most of our data is in that. Our results are in that region. Yeah, that's a summary of our contributions, but I'll skip that. And I just thought this might be good. So it's just some code for the graph neural network layer and a summary, and I'll stop at that point. Thank you.
All right. Thanks, Guyan. That was good. And do we have any questions for Guyan? So just wanted to point out, we've seen explicitly, you might be wondering where the transformer is in this work. One of the important things about transformers is the fact that it uses attention inside it. And that's an incredibly important, so you have words and you link all the possible combinations of words, but then you're learning the attention between where to pay attention between the data. And that's where in graphs, you can learn the attention between the nodes. And of course, both Lou and Guyan have shown how to do that in various ways. And the enhancement and problems that you have that have recently been solved.
Yeah, Shakes, just to add on to that, how
Yeah.
transformers can be used. The typical or normal way that we normally apply transformers is we take the same graph neural network here, and we do something called random walks. We start from one node and just keep, walking along the connections, and that path can be considered as one of these text sentences. So this path can be taken as this and then fed onto the into a standard transformer, and you could just learn the same encoding. So what we need to learn is, given some node, how to get that encoding function for the representations, which is basically we call this a language model here, kind of thing. So you use like random walks, or there's also something called meta paths. Either way, you just convert this into a collection of paths and just use these text encoding concepts with a transformer.
Okay, great. Yep. So that's the way to use the traditional transformer as well. All right. Any other questions for Guyan? We have one more talk remaining. And that's when we talk about multimodal learning. So when you have more than one type of data. So far we've seen either graphs themselves, images themselves, or text themselves. What happens when you have multiple sources? And that's what Karen is going to cover next. So thanks, Guyan, for your talk. We'll move on to the next speaker. And Karen is going to talk about how to handle multiple types of data. And she will be reviewing a paper, not by UQ, but outside. And yeah. So whenever you're ready.
Hi, Shakes. Can you see my screen?
Yeah, you can see it's not anymore.
Oh, yeah, I'll just. Can you see my screen?
Yes, but no longer the first page. There we go. Right. Yep.
Yeah.
All right. Thanks, Karen. Go ahead whenever you're ready.
Yeah, thanks for the introduction. So today I'll talk about transformers application in disease prediction using multimodality data. So this is the paper that I will be talking about. It's called the clinically inspired multi-agent transformer for the NE-OA trajectory forecasting. So basically, NE-OA is a disease which can be seen from the narrowing of joint space, as you can see in figure 1 here. And it can be progressive over time. And diagnosing OA at an early stage can be beneficial because it allows the slowing down of the disease, and it can provide proper treatment. So the prediction of the future trajectory is really important. And this paper is talking about the prediction of the trajectory over time. So the main method that has been used in this paper is called clinically inspired multi-agent transformer. So basically, the whole framework is inspired by a clinical process, which means you have 2 agents as it says, multi-agent here. One is considered as GP and the other one is considered as a radiologist. So basically the radiologist firstly analyze the X-ray images so that it can provide a report or provides a representation of the image features. And then the GP takes the makes the prognosis, which means the GP consider the radiologist feature that provided by the radiologist, and also they take into account of different informations which not necessarily need to be images. It can be other informations from the patient. So this is an overview of that method. So basically you have the imaging data, as you can see here, it's an X-ray image, and it can be like this is an example of X-ray image, but in their other works or extension of the work, it can be other images for different disease as a general framework. And for the clinical variables, they consider the age, sex, BMI. So basically they pre-process the imaging data into a transformer and then provide a visual description, and then using similar method to process all those clinical information, and then give these features to another transformer and do the prediction. And specifically, this is a detailed look of that framework. They have 3 transformer blocks. The first transformer is called transformer R, which acts as a radiologist. The second one is called context block, which deal with the non-image features. And then they produce the feature H here, HR and HC. And then they put all those features into another transformer, which is the P here. And the P transformer is used to make the decision. And in detail, this is a architecture or detailed look of the radiologist block. So it's basically a visual image transformer, the VIT. It has the similar structure of VIT as Marlon introduced before. So the input of these are 2 components. One is an empty space used to make a prediction. So it's live for the class prediction. And then there are some features that extracted from the CNNs. So they use ResNet in this paper, but it can be other network to extract the image features. And then these image features go through the positional embedding and go through the multi-head self-attention, and also like the layer norm and MLP to get HR, which is a representation. And then this HR along with the HC goes through a P block, which is another VIT. So in terms of the HC here, it's used a VIT as well. So basically they use 3 VIT. So for the non-image information, they have all these features and they are clinical variables, and they can use the learnable embedding to represent all these clinical variables, and then let it go through the multi-head attention and also the layer norm as mentioned before, and get a HC feature, and then all these features combined together to go through the final VIT to make a decision. And they have conducted experiments on the OAI datasets, which include more than 4,000 of patients, and they have the timeline of 1 year, 2 year, as it shows here. And the image information they used for these experiments is X-ray, and also the non-image information are used like these ones, and they are both extendable to other disease and other modalities. So this is the experimental results. So basically they compare with all the other methods, FCN, GRU, L, STM, and the purple lines here is their results. So the upper part is the accuracy, and the lower part is the root mean square error. The upper part is the higher the better, and the lower part, the B here, is the error. So which means the lower the better. You can see that the purple lines, which is their proposed method, can outperform other methods quite significantly, especially in the lower results here, the lower image here. And also they try to interpret the results to see if the network is doing something as expected. So they visualize the attention maps of the third component, the prediction module, the GP's module. And you can see this is a attention map that focusing on the joint area, which you can examine if it's narrowed down, which means that relates to the disease progression. And this is a contribution of the variable, like different variables they used. Yeah, so that's the interpretable results. So in conclusion, in that paper, they proposed a multi-agent transformer, which means they use 3 transformers to deal with 3 sources of information, and they achieved better results on the NeOA prediction. So that's all about that paper. Are there any questions?
Thanks, Karen. Any questions for Karen? So there's a lot of transformers in there. Did they talk about run times and training times and all those sorts of things?
No, not in this paper. Because I think it's conference 1, it has 4-page limitation, so they don't really have extra space. Yeah, but it's more like the idea that using 3 transformer dealing with 3 source of information can be beneficial.
Yep. Any questions? Any other questions for Karen? So I guess the main gist there is, transformers are very flexible architecture. You can combine them together. You already saw with Linfeng as well, you can combine different views of the same data. In 3D data for imaging, that was beneficial, but it may also be in your case as well, where you look at the data different ways. And of course, if you have different sources of data. So hopefully we've covered a number of those cases. Yeah, okay. So if we don't have any more questions, we might conclude the session. So thanks for all the speakers today for taking time out to talk to us about your work. Now, some of it may not have made sense, and that's fine. I guess the benefit of the recordings are that on Friday, we'll cover a lot more of the technical details of transformers. And then if you still have some hazy ideas, you can come back to this, more experienced by then, and come back to this recording. Also, feel free to reach out to the speakers if you have questions as well. Next week, we'll also have some more journal club on different topics, and I'll set out the agenda for that later on in the week. All right. Thank you very much for your attention, and we'll end the session there. Thanks. Thank you.
Thank you.